Hi students, this is Monica Bansal from Bullseye. I have been guiding students on various aspects of quantitative aptitude for last 10 years. Today's topic is sequence and series. We are going to discuss some special kind of sequences that is a section of advanced algebra. However, to ensure the better understanding of the concept, it is imperative to know the basics of arithmetic progression and geometric progression. So let us have an overview of the session. First of all, there will be questions based on AGP series. We call it arithmetico-geometric progression. Then you will have some question based on some special series. Then you will have some practice questions. So let us move to AGP series. Question says, let S is equal to 2 by 3 plus 5 by 3 square plus 8 by 3 cube plus 11 by 3 raised to power 4 plus so on up to infinity. We want to calculate S. We want to find the sum of infinitely many terms. As you can see in the numerator, we have an arithmetic progression. What is the first term here? That is 2. What is the common difference? That is 3. And in the denominator, we have a geometric progression. What is the first term of this GP? 1 by 3. And what is a common ratio? That is 1 by 3 again. This is our first term and this is the common ratio of the GP. So that is a combination of arithmetic progression and geometric progression. So we call them AGP series, arithmetico-geometric progression. We have a particular method to solve these kind of sums. Let us see the method, then we'll come to the shortcut. First of all, we will multiply the whole series, the whole sequence by common ratio, which is 1 by 3 in this case. So it will become 1 by 3s. Now, what will be the first term in this case? It will be 2 by 3 square. We will leave the first place empty. We will write the first term here. Then take the subtraction. It will become 2 by 3s, first term as it is. Now 5 minus 2, 3, since we have same denominator. Now you can see that second term onwards, we have a pure GP, pure geometric progression. And there are infinitely many terms in that GP. We have a formula to calculate sum of infinitely many terms of a GP. What is the formula? That is A upon 1 minus R, where A stands for first term and R stands for common ratio. So we can write 2 by 3s is equal to first term again as it is 2 by 3 plus. Now we will apply the formula. So it will become 3 by 3 square, that is A upon 1 minus R, which is 1 by 3 in this case. If you solve it, you will get S is equal to 7 by 4. I am leaving the calculation part for you. So this is the answer in this case, 7 by 4. Now come to the shortcut. This is direct formula for infinite sum of an AGP. It says as infinity, sum of infinitely many terms. This is equal to AB upon 1 minus R plus DBR upon 1 minus R whole square, where A is the first term of the AP, B is the first term of the GP, D is the common difference of the AP, and R is the common ratio of the GP. Let us apply this shortcut. I'm taking the previous sum only. So if we apply this formula, S infinity will become A into B divided by 1 minus R plus DB R upon 1 minus R whole square. So if you solve it, you will get the same answer, which comes out to be 7 by 4. Now let us move further. There is one more question based on AGP series. Again, we want to find the sum 1 by 5 plus 3 by 5 square plus 6 by 5 cube plus 10 upon 5 raised to power 4 plus 15 upon 5 raised to power 5 and so on up to infinity. In the numerator, if we take the difference, here the difference is 2, then we have a difference of 3, not the same difference, 4, 5. So that is not a direct question of AGP. So we cannot apply the direct formula for finding the infinitely many terms sum of AGP. But in the second step, if we see, it becomes an AP, arithmetic progression. So how can we solve these kind of sums? We'll apply the same technique. Let S is equal to 1 by 5 plus 3 by 5 square plus 6 by 5 cube plus 10 by 5 raised to power 4 and so on up to infinity. What is the common ratio here? The common ratio is 1 by 5. So I'm going to multiply the whole series with the common ratio. So the first term will become 1 by 5 square. Again, leave the first place. We will write 1 by 5 square here. 3 by 5 cube. 6 by 5 raised to power 4 and so on up to infinity. Then we will take the subtraction. Subtraction will become 4 by 5s. First term as it is. Now what is, since the denominators are same, we can take subtraction of numerators only. It comes out to be 2 by 5 square. Then it will become 3 by 5 cube. Then it will become 4 by 5 raised to power 4, so on up to infinity. Again, you can see in the numerator we have a direct AP. So we can apply formula here. To apply the formula, we will write the first term of AP, which is 1. What is the common difference? That is 1 again. What is B? B means first term of the GP. It is 1 by 5. And what is the common ratio? That is 1 by 5 again. So we will apply the formula here, which comes out to be AB upon 1 minus R plus DBR upon 1 minus R its whole square. So if you solve it, you will get the answer. Again, I'm leaving the calculation part. S comes out to be 25 by 64, and that is the final answer in this case. Now let us move to next question. Again, a new kind of series. We want to find the sum of the series 1 upon 2 into 5 plus 1 upon 5 into 8 plus 1 upon 8 into 11 plus so on up to plus 1 upon 35 into 38. There is a pattern going on. If you observe, what is the difference every time? This is 3. 1 upon 2 into 5, 2 plus 3 will become 5, 5 plus 3 will become 8 and so on. So how to solve these kind of sums? Again, there is a method. In this case, you will take the difference. As you can see, this is 3. So we will multiply and divide the whole series by 3. I mean, it will become 1 by 3. We are dividing it by 3 and we are multiplying it by 3. So it will become 3 upon 2 into 5 plus 3 upon 5 into 8 plus so on up to 3 upon 35 into 38. What is the usage of this? See, now this 3 can be written as 5 minus 2. It can be written as 8 minus 5. As you can see here, we have 5 into 8. That's why I have written this as 8 minus 5. Since we have in denominator 38 into 35, that's why we are writing it as 38 minus 35. So if we take the very first term, it will become 5 minus 2 upon 2 into 5. If we separate them, it will become this 5 upon 2 into 5 minus 2 upon 2 into 5. Similarly, the next term will be 8 upon 5 into 8 minus 5 upon 5 into 8. The last term will become 38 upon 35 into 38 minus 35 upon 35 into 38. Now see the magic. What is the usage of all these things? Now it will become 1 upon 2 minus 1 upon 5. They got cancelled. Plus 1 upon 5 minus 1 upon 8. Plus 1 upon 8 minus 1 upon 11. The last term will become 1 upon 35 minus 1 upon 38. Now, if we take the second term of first bracket and the first term of second bracket, they got cancelled. So, all the term will get cancelled except the first and the last term, and this will happen always. So my answer will become 1 by 3 half minus 1 upon 38. If we solve it, we will get 3 by 19. That will be the final answer in this case. So directly we can learn, we can assume that whenever the last term is mentioned, we will take only the first term and the last term. So my answer will become half minus 1 upon 38 into 1 upon the difference. What is the difference here? 3 will be the difference here. So that will be the final answer in this case. 3 by 19, this is the answer. Now let us move further. A huge question. It says there are 8 4 3 6 balls, each with a radius of 1 unit, stacked in a pile with 1 ball on top, 3 balls in second layer, 6 in third layer, 10th in fourth layer, and so on. Find the number of layers in the pile. So let us understand the meaning of this question. We have some balls in a pile. We have 1 in the first pile, then 3 in the second layer, then 6 in the third layer, and 10 in the fourth layer, and we don't know the number of layers here. That is a question. So let us say there are n layers. So I'm writing this as n terms, and this total comes out to be 8 4 3 6. We want to calculate n here. So let us see. We will take the help of series again. It says 1 3 6 10, so on up to n terms. This is not a direct AP, GP or AGP series, but we can observe that the difference here is 2, 3, 4 and so on up to. How can we solve these kind of series? We will try to write the nth term of these kind of series. As we can see that T1 is 1 here, I mean the first term. T2 is 3 here, that is 1 plus 2. We are adding 2 to first term. Then we have T3, that is 1 plus 2 plus 3. Then we have T4, which is 1 plus 2 plus 3 plus 4. So by generalizing, we can say that Tn will be nothing but summation n. See, the first term we are taking only 1, the second term we are taking 1 plus 2, and in the third term we are taking sum of all natural numbers up to 3. In the fourth term we are taking sum of natural numbers up to 4. So we can generalize that in Tn we will take sum of first n natural numbers. So it will become sigma n. We have a formula for this. This is n into n plus 1 by 2. That is our nth term. Now we want to write Sn here, sum of n terms. So how can we do this? Nth term can be written as half into n square plus n. So if we apply sigma here, it will become half sigma n square plus sigma n. How come? Let us see. See, our Tn is half n square plus n. What will be T1? If we write in this manner, it will be 1 square plus 1. What will be T2? It will be half of 2 square plus 2. And so on up to Tn. It will be half of n square plus n. We want to calculate Sn. What do you mean by Sn? That is sum of first n terms. So if we combine them, we will get 1 square plus 2 square plus so on up to n square. That is the first column. Plus, now the remaining thing, 1 plus 2 plus so on up to n. So it comes out to be half of sigma n square plus sigma n. Let us solve this. What is sigma n square formula? It is n into n plus 1 into 2n plus 1 divided by 6 plus what is sigma n formula? N into n plus 1 divided by 2. So first of all, we will take n into n plus 1 divided by 2 common. We will be left with 2n plus 1 divided by 3 plus 1, which will become n into n plus 1 divided by 4 into 2n plus 4 divided by 3. If we solve it, the final expression will become n into n plus 1 into n plus 2, because 2 will be common here, divided by 6. Now this sum of n terms, if we are considering that there will be n layers, this is given as 8, 4, 3, 6. So if we solve it, we'll get the answer. We can go by options. By taking options, we can see that the second option is the answer. So there will be 36 layers in that pile. Let's move further. A nice question on Fibonacci series. It says, find the number of all 10-digit natural numbers made by using digits 3 and 5 only, such that no 2 3s are consecutive. No 2 3s are together. So what is our conventional approach? We'll try to make cases. Since it says that no 2 3s are together consecutive, so we can take number of 5s 10 and there will be no 3. How many such numbers are possible? There is only one number, that is all 5s. Then we will take the second case where number of 5s are 9 and there is only one 3. So 3 can occupy any of the 10 places. That's why there are 10 numbers possible. If we keep on going in such manner, we will have many cases, and by adding all of them, we will get 144 as the answer. But it is cumbersome, so we will make use of a beautiful series which is known as Fibonacci series. See, we'll go by taking smaller length of the number. Let us take there is only one digit number. So I am applying the same condition that we want to make numbers by using only 3 and 5 and no 2 3s are consecutive. So we are talking about one digit number. So how many numbers are possible? Only 2. Either it will be 3 or it will be 5. So in total, how many numbers are possible? 2. What about if I take 2-digit numbers? So if we make cases, since our condition is no 2 3s are consecutive, number can be 55, it can be 53, it can be 35, but it cannot be 33 because of the condition given. So how many such numbers are possible? They are 3 in total. So we have seen, if we are talking about one digit such number, they are 2 in number. If we are talking about 2-digit numbers, they are 3 in total. What about if we take 3-digit numbers? Either my number will start with a 5 or my number will start with a 3, and there are 2 places remaining. So If we take the first case in which the number is starting with 5, remaining two places are nothing but all the two-digit numbers which are satisfying the same condition. And we have calculated that there are 3 such numbers. Once again, if we are starting our number by 5, either my number will be 555, or it will be 553, or it will be 535. So these are nothing but the case which we have calculated previously. Now let us come to the second case where my number is starting with a 3. After 3 you cannot take a 3 because of that condition that no two 3's are consecutive. So we have to take a 5 on the second place. So the remaining numbers are nothing but all the one-digit number which are satisfying this condition, and we have calculated it previously. So how many such 3-digit numbers are possible? They are 5 in total. Once again, if we talk about 4-digit numbers, either my number will start with a 5 or my number will start with a 3. Since we are talking about 4-digit numbers, 3 places are remaining. So if we take the very first case where the number is starting with a 5, we still have 3 places to fill. So these 3 places are nothing but all the 3-digit numbers which are satisfying the same conditions, and we have calculated those in the previous case. They are 5 in total. Similarly, if we take the next case where our number is starting with a 3, after 3 you cannot take a 3, that's why we will put a 5 here. So we are talking about all the 2-digit numbers which are satisfying the same condition that we have calculated previously. So it will be nothing but in total 8. So every time we are calculating, we are increasing the length of the number. Suppose we are calculating 5-digit numbers. It will be nothing but sum of previous 2 places. So we can say that if we talk about 1-digit number, they were 2. If we talk about 2-digit number, they were 3. 3-digit, that is nothing but the total of previous 2 terms, that was 5. 4-digit, again the sum of previous 2 terms, that is 8. 3 plus 5. If we go on in this manner, we can calculate 10-digit number which comes out to be 144, and that was the answer in this question. So this kind of series is known as Fibonacci series. Very, very interesting and important series where the nth term is sum of previous 2 terms. Only first 2 terms are defined in the series, and the third term onwards we can write the whole series because every term is nothing but sum of previous 2 terms. So applying this technique, we can calculate the number of all 10-digit numbers in a jiffy, because we have to calculate a series only, not so many cases. So answer is 144 in this case. Now these are some practice questions. And these are the answers. For more videos and more concepts, log on to hitbullseye.com. Thank you so much. Happy learning.